Hey guys, this is lesson 6.8. We're going to go into more applications of derivatives. And so this lesson will be our last one for Unit 6. Then we're going to get into Unit 7, which is special derivatives. Okay, so in this video, I'm going to be talking about position, velocity, and acceleration. Now, those terms might seem very familiar if you've taken physics. That's perfect. I love that we can make connections between different courses because the material doesn't change. All the rules are pretty much the same because fundamentally, math is math, right? So, taking a look at the title, position, what we use in calculus is usually S at t. I have no idea why they use s, they just do. And so the velocity function is the derivative of the position function. So s prime t is the same as v at t. The acceleration function is the double derivative of the original position graph, or in other words, the derivative of the velocity graph. Okay, so we have the first derivative and the second derivative compared to the position. Now, what I'm going to do is just show you what all of those mean. I am going to be drawing from my palette of colors quite a bit, so I'm sorry if that's a little bit distracting to you. So the position, if we have an object, is right there on the left. So our position is going to, our object is going to start on the left-hand side, and then maybe it's moving towards the right. So we can actually map that on the right-hand side through a graph. We'll just pretend that the object is starting right over here, and we'll start to move, okay? Because this is a graph that shows the position throughout the time. As you can see, it's an S versus T graph, so it's a position graph. Now the movement itself could be in a certain direction, right, or it could be left. So that is the velocity. It's going at a certain velocity in a certain direction. Okay, now your acceleration will be how fast. Is it slow and then all of a sudden very fast in a certain direction? We don't know. So we're going to have to analyze those kinds of things. But I hope you can see the difference between your position, your velocity, and the acceleration. So the comparison of those velocities, which is your acceleration. I want you to understand this graph a little bit more first before we get into trying to answer any of the questions. So this is a position time graph. And again, for example, if time was 1 second or 1 minute, why don't we just say 1 minute? Okay, so at 1 minute, your object is going to be about 3.2. Okay, so 3.2 meters away. At 2 seconds, it's even farther away. 4.1, 4.2, whatever. It's farther away from your original position. Okay, so we'll just say since your original position was left, anything that's farther means going towards the right. At 7, what do we say, minutes? It's going to be about 5 meters away. So notice that at sometimes it does look like it's going farther and farther away, but if we choose say something like 4, it's actually very close to us again. It didn't go farther, it actually came back. So it looks like it was going farther and farther right, then it came back left again, and now it's going to the right again. So all of this is in relation to the left and right. Okay, let's get rid of all of that scratch work so that you guys can see. All right, let's start answering some of the questions. Is the object going faster at point E or F? What are they asking you for? Are they asking you for the position, the velocity, or the acceleration? So going faster, fast means some sort of velocity. And that means I want to compare, now velocity is my slope of my position graph. So I'm comparing the slopes. I want to know what the slope at E looks like versus the slope of the tangent at F. When we compare the two, how do we know which one is going faster? So going faster means AKA steeper. Which one is the steeper one? As they go through the same amount of time, which one is higher? So this is the same amount of time. This one looks like it's covered more distance. And so the rate of increase is basically, it's faster at F because F is the steeper one. So therefore, It's going to be going faster at f. Now, when is the object moving to the right? Okay, so we talked about that already. Get rid of all of this. If we started, and this is the left, and as time goes on, we're actually moving farther away, we're going to pretend that that's going towards the right because that's what this original diagram was indicating. Okay, so in this particular part where we're increasing in slope, it looks like we're going farther and farther away from our original point. When we go decreasing slope, we're going closer to our point again because the distance from the t-axis is decreasing. But then on this part of the graph, we're actually getting farther away from the t-axis. And so we're getting farther away from our original position. That means that when is the object moving to the right? It's actually moving to the right whenever we have an increase, like our positive slope. So that would be from O all the way to B, and from D all the way to G. Okay, now what I'm going to do is I'm going to take a small little picture, so there's my picture, of the graph because I want to answer some of these questions. Describe at each interval of the graph when is the object speeding up or slowing down. So speeding up and slowing down is not just the velocity, it's the comparison of the velocities. So this is actually talking about your acceleration. So you're going to compare each of your slopes of your tangents in all of the different sections. Let's start from O to A. When we talk about our slopes, this is a very steep slope, and then it gets less steep, and it gets less steep. Notice that it's trying to get towards that peak at B, and you know that the slope at B is going to be 0. So your slopes are decreasing in value, which means that we're slowing down. Okay, now from A to B, you are going to continue slowing down because you know at B it's going to be flat. This is a slope of 0. Right? So we're going to say slowing down again. And eventually at B, you're going to come to a stop. All right, now after that stop from B to C, you're going to start increasing your speed again, but your direction might have changed. You're now going back towards your original position, but in either sense, your slope is increasing in value in a negative direction. So you're actually still speeding up, but a negative slope means you're going in the opposite direction now. Okay, now from C to D, you're still going negative, but at D, you're going to be at a 0. So it looks like it's negative, less negative, less negative. Getting towards a 0 means, again, if you have any sort of a speeding up and you're trying to go towards 0, you're actually slowing down. Okay, and again at D, you're going to come to a stop. Now from D to E, you're going from 0 at D, increasing, increasing, increasing. Okay, so you're speeding up again. Since it's a positive, you're actually going away from the original position. Okay, so we'll say away. Or in other words, I think if you're going to use what they were talking about before, like left and right, you're technically going to the right based on your original diagram of that circle at the beginning. Okay, now from E to F, you're getting even steeper, even steeper. So still speeding up. And lastly, from F to G, you know that G is going to be a flat slope. So since this is super positive, you're going to go less positive, less positive, less positive towards a 0. That must be slowing down. and then at G, you'll stop. Okay, so I hope that that makes a lot of sense. Now let's go into some more concepts. So when we're combining position, velocity, and acceleration, we get something where we can ask you certain types of application questions. And so we could just talk about moving towards something, slowing down, speeding up, and so on. And this actually touches upon each of the position, velocity, and the acceleration. So let's kind of explain it one more time, but maybe with the number one line. So we'll just say this is, I don't know, like your house or the origin, like your starting point. Okay, and as a number line, we'll go, this is +1, +2, +3. This is going to be -1, -2, -3. Okay? Now let's just talk about the position first. So position positive. When your S value is greater than 0, so positive, it means that it's somewhere in this region. It's positive. Okay, so it's on the right, and your position might be, here is my original, like, that's where my object is. It's not really moving at the moment. Okay, now if you're talking about less than 0, you're talking about your object is originally placed somewhere on this side of the number line. Okay, now let's talk about velocity. If velocity is greater than 0, it means that wherever your original object was placed, it's now moving in the right-hand direction. Okay, now this guy, less than 0, if your velocity is less than 0, it actually means that you're moving in a left position. It doesn't, sorry, a left direction. It doesn't mean that your position is negative, because remember, position being negative would be on this side of the number line, but this could also move in a negative direction. Okay, let's talk about acceleration. So an acceleration is a little bit more difficult to explain. Think about faster and faster. Okay, so if acceleration is greater than 0, you're going faster and faster in a right direction. So it's kind of like velocity where you're moving to the right, but it's the speed at which you're moving. It's the rate of your movement. So it is the derivative of your derivative. Okay, now if it's less than 0, it means you're actually moving faster and faster towards the left. So you're pushing faster and faster towards the left direction. Now this gives rise to a combination. If I decide to combine some of these together, you get certain kinds of movements and accelerations. So let me explain. If you're moving towards the origin, I went a little bit too far. Let me show you with the number line again. So we'll get rid of all this. Okay, number 1 is saying, in either of these scenarios, you're going to get a movement towards the origin. So let me explain. If you have your original position, your S is less than 0, which means that it's somewhere in the negative region, right? That's your position. Now, if your velocity is greater than 0, which means it's going towards the right-hand side, you're going to be moving towards the origin. Just as if you decided in the other case, so this guy right over here, if your position is positive, so somewhere on the right-hand side, and then your velocity is going to be less than 0, which means it's going towards negatives, going towards the left, that means that it's going towards the origin. So in either of these cases, you'll see that you're going towards the origin. Now, if you take a look at number 2 says moving away from the origin. So this is the opposite. Let's just say that in the original case, you have a left position, okay, so in the negatives, but then what you're going to do is you're going to move this way because your velocity is a negative. So if that's the case, you're actually going away from the origin. In case number 2, you have a positive position, Okay, but you're going to have a positive velocity as well, and so you're moving away from the origin again. So these should kind of make sense to you just through the diagram itself. All right, so let's get rid of those. Let's get rid of this. Get rid of all that. I think what I'm going to show you is both this graphically and then also algebraically. But I do want to give you a rule. So why don't we say, if these guys are opposites, do you see how these are opposites? If I multiply them, it's almost as if this is going to be a negative number for S, this is going to be a positive number for V, this is going to be a positive number for S and a negative number for V. So when I multiply a negative and positive, obviously I'm going to get a negative. So if you take your position and you multiply your velocity, you're going to get something less than 0. But since these guys are actually going in the same direction, both of these are negatives, these guys are going in the same direction, positives. Okay, so S times V is going to be a positive number. All right, now going into these ones, slowing down and speeding up. Let me just start with speeding up because it's a little bit easier to understand. If your velocity is positive and you're accelerating in that same direction, obviously you're actually going to be speeding up. Okay, even though these are both negatives, you're still going to be getting a positive answer. If you multiply them together, you're going to get a speeding up, but maybe in a different direction. So V times A is going to give you a positive. Slowing down is when you have them in an opposite direction. I don't know if I should say direction. I just mean that you'll get opposite symbols. Sorry if I was a little bit unclear. But basically what happens is when you take your V and you multiply your A and you get a negative number, you're going to have something slowing down. Okay, so the direction of motion is really based upon your position and your velocity. These two up here are the ones that deal, whoops, okay, that was weird. These two, why is it doing that? That's so strange. Smartboard, why are you making me look like a fool? Anyways, 1 and 2, these two are the ones that tell you about your direction of motion, versus 3 and 4 are the ones that tell you if you're speeding up or slowing down, and they have to do with your velocity and your acceleration. So let's take a look at an example. I'm going to show you first graphically, and then I'll show you algebraically. Okay, so number 1, given a certain function, this is the position function. Given this function is the path of travel for an object, determine the time. So they're asking you, what is the time in the intervals where we're slowing down? Okay, so slowing down, we had said on the previous slide that we have two cases. We either have V is positive, A is negative, or we have V is negative, A is positive. Okay, so I'm going to take a look at the two, but first what I want to do is look at each of the graphs. And so what I did was I took the original position graph, I took the derivative to find the velocity graph, and then I took the derivative of the velocity graph to find my acceleration graph. All right, now we had talked about the graphs before. If I set this equal to 0, then I can figure out that time is 0. And from this one, time is 6. So I basically get the two t-intercepts right here and here. Now, those two are where I'm going to have, the peaks. The peaks are where I'm going to have a slope of 0. So these 2 points right here are actually important because they're going to be my intercepts for my slope function. Now this part right here, where the slope is 0, is going to be where I'm going to have my intercept of my derivative function. Okay, so I posted a video just on how to graph, but I'm hoping that this, you see some of the things that you had seen in the previous videos. So anyways, each of these graphs, what I'm going to do is I'm just going to compare the purple and the light purple graphs because I want to see where these two things happen. Okay, so let's just overlay two of the purples on top of each other. Okay, in case number 1, I'm looking for when is the velocity greater than 0? So when is the velocity positive? The velocity graph is a darker purple, and so it looks like it has positive y values here and here, which I've stated right here. T belongs to negative infinity to 0, and then from 4 to infinity. Now, when I'm looking at this, I want to know when is the lighter purple function less than 0, as in when are the y values negative? And so since this is my intercept, anywhere down here has negative y values. So from negative infinity to 2, I'm going to have an acceleration of less than 0. Now, when do both of these conditions happen at the same time? i.e., when, look at both of look at the graphs and see where the green is overlapped for both functions. In which region? Let me use some red. So in this region, that's not red. Smartboard is not liking me today. In this general region right here, notice that both the graph is green. Nowhere else in any region are both of the green parts of the graph actually overlapping. And so this is my combined answer right here, from negative infinity all the way to 0, which actually doesn't really make sense. I mean, t represents time, right? So negative infinity to 0, that's negative time. That doesn't make sense. So I'm going to scrap this case and I'm going to go on to case 2. We're going to do the same thing. When is velocity less than 0? So taking a look at the velocity graph, these are my negative y values. When is the graph for the lighter purple greater than 0? So my intercept over here, anything above the t-axis. So I have both of those right here. T belongs to 0 to 4 for the darker purple. T belongs to 2 to infinity for the lighter purple. Now where does that overlap? Now notice that it actually overlaps only in this region, this box right here. So both of the greens are overlapping. That means that from 2 to 4 seconds, that's where the object is actually slowing down. That's all graphically, but I really want you to be able to see it algebraically. Okay, so let's try this again. Slowing down. What does that actually mean? Well, we said when velocity multiplied by the acceleration is less than 0. Okay, so what we're going to do is we're going to have all of our functions. So again, position function was this guy. I got my velocity acceleration, which is s prime. So s prime at t is your velocity function, which is 3t squared minus 12t. Okay, and then we have your acceleration. So acceleration is the double prime of your position graph. Acceleration is derivative of the above. Okay, so once you have all three of your functions, we want to figure out this guy. Okay, so let's take our velocity function and multiply it by our acceleration. So velocity is 3t squared minus 12t multiplied by our acceleration, which is 6t minus 12. And we want to prove, or not really prove, we want to find where that is less than 0, right? Less than 0. Okay, now you've done something like this in advanced functions before, or in the prerequisite to this course. What we want to do is we want to figure out where the t-intercepts are. Okay, so I'm going to start to factor a little bit, and this should look somewhat familiar. So just from this purple part, it looks like I can take out a 3t, and I'm left with t minus 4. From this lighter purple part, I can take out a 6, and I'm going to be left with t minus 2. Now I'm going to clean that up a little bit by bringing maybe the 6 all the way to the front and multiplying it. So 18t, I still have the t minus 4, and I have the t minus 2. So from here already, I can already solve for my t-intercepts. This guy's going to give me t equals to 0. This one's going to give me a t equals 4. And this one's going to give me a t equals to 2. So those are all of my intercepts. And from there, let's make one of these charts where we go from negative infinity all the way to 0. Don't include it though, okay, because it's where the slope is 0, and so I don't want to include it. 0 to 2, because we're going to go in order, right? 2 to 4, and then 4 to infinity. Do you guys remember one of these? Like one of these big plus minus chart things? Okay, we got all of the different parts, the 18t, okay, that's this guy. The t minus 4, that's this guy. And then the t minus 2, that's that guy. And we're going to test each of those. I don't even know if that's really not straight. That's okay. It's a Friday, I don't care. We're going to test each of these in each of the regions above to find out what v multiply a is. Okay, so you'll start to see when you plug in the numbers, choosing a number from negative infinity to 0 in each of the regions is going to be negative. From 0 to 2, maybe I would choose 1 and plug it into each of the regions on the left. You're going to get a positive, negative, negative. Okay, maybe choosing 3 in my next region of my domain and plugging it in, I'm going to get a plus, a minus, and a plus. And then maybe a really ginormous number like 100, plugging it in, I'm going to get all pluses. So at the end, I'm going to get a negative, a positive, a negative, and a positive. And so these two are where v at a is less than 0. So this one obviously doesn't make sense. That was from my case 1. If you recall the graphs, it doesn't make sense because there's no such time from negative infinity to 0. However, from 2 to 4 does make sense. Therefore, t belongs from 2 to 4. So I hope this ties in not only the graphing, but also things that you've learned from advanced functions in the previous course. And we're going to get into crazier derivatives in the next unit. So derivatives of trig, derivatives of log, and so on, like fun stuff. Okay, so today is a Friday. I hope you have a fantastic weekend.